Hello, good morning everyone. Okay, so welcome to our tutorial 2. So let's let me see how many. Yeah, okay, so about 33 of you all are in already. So let's get started. I think the rest should be joining us soon. Okay, so in today's tutorial, we are going to cover the concepts that we did in the last few studios, which was mostly timers, correct? So one was on the PWM, the other was on the timer and the interrupts, all right? And I think we also discussed some of the common, misunderstandings that most students were having, all right? And if you have questions, please ask me along the way, all right? So that probably the question you have, it might be a similar question that somebody else is also having, all right? So just ask the question or you can type it out and then we can take it from there. Okay, and as always, have your data sheet. Okay, the Atmel microcontroller data sheet with you at all times. Okay, so it's always good to know where to find the information. All right, so in our slides, we extract, okay, whatever we provide to you is from the data sheet. Okay, so we extract the data from the data sheet and then we sort of summarize and give you the key points to do all this. All right, but you must also be comfortable and confident to look at it yourself and figure out how to control or program a particular peripheral. Okay, so even this Arduino Uno, we are not covering all of it. All right, so for example, in next week's studio, I hope you saw the announcement. All right, that next Monday, Tuesday will be the ADC studio. All right, we are shifting it around a bit. All right, so we're going to cover the ADC module. All right, so this is a fairly simple microcontroller. So we cover most of it, but maybe things like analog comparator here, we don't cover. Serial peripheral interface SPI, we don't cover. All right, but these are all important peripherals, correct? Quite useful peripherals. So it is good to have some self challenge, you know, to try and figure out, okay, how do I program this, how do I program that, and so on, and try it out. Okay. Of course, you can always refer to online resources and sample code. Okay, but as I always say, don't copy blindly. All right, even if it works, make sure you understand what's going on. All right, so that in the future when you are taking up your own microcontroller and you want to interface and build stuff, you have the confidence to do it. All right, and I think one of the key things of this module, as well as in future when you do 2271 and all, is to not be overly reliant on library functions that are provided. All right, of course they are very, very useful, okay, because they help to abstract everything and make our life very easy. Okay, but in the real world, in the industry, we don't use or we don't rely on library functions most of the time. Or you're expected to develop your own code. All right, and that can only happen when you understand how the underlying hardware works. All right, so always try to get a better and deeper understanding. So we introduce you to those concepts here, and you will carry on in other modules as well. Okay, so let's get started. So before we go into the tutorial question, I just want to do a quick recap of some of the things we did in the studio. So these are activities which we have done, all right, but I just want to clarify what is happening. All right, so one of the things that we did in the PWM studio is to drive the motor. All right, so the motor was driven using this chip called the DRV8833. Okay, so you will see this again when you're assembling your final robot. This module as well as in another module, 2271. All right, so this is a fairly compact and useful motor driver chip. And what is this dual H-bridge motor driver chip all about? Okay, so it's about, so if you look at the connection, all right, we call it a H-bridge because we have this shape of a H. Okay, it looks like a shape of a H. And basically what happens is, if you see down here, basically a motor can spin in both directions, all right, clockwise or anti-clockwise. And it all depends on which way the current flows. So this H-bridge sort of allows us to control a pair of switches, such that if this alternate pair are closed, then current flows in this direction. All right, and it spins in one particular sort of direction, okay, orientation. And if I flip to the other two switches, it flows in the opposite direction. All right, so basically that is what a H bridge is all about. All right, and of course the internal structure is abstracted into a very simple connection. All right, so if you look down here, basically A in 1, A in 2 control AR1 and AR2. Okay, and for motor to spin in any direction, one side must be positive, the other side must be ground. All right, so that is why, okay, if let's say my A in 1 is having the PWM signal, okay, and my A in 2 is grounded, okay, then the current will flow in this direction and motor will spin in this way. Okay, if it is swapped around, then current flows in the opposite direction. Okay, so this is basically how the H bridge works. You just need to make sure that one side is having the PWM, the other side is grounded. All right, so current flows in one particular direction only. Okay, and of course, the other reason why we want a H bridge driver and not directly drive a motor. Okay, you can directly drive a DC motor. Okay, I'm not sure how many of you play with those small self-assembly cars or have played with it in the past. All right, so if you open up some of those small remote control cars or self-assembly cars, you will see they have very small DC motors. Okay, so they're very small, very compact, and those kind of motors can easily be driven with a simple 5 volts supply or 9 volts battery and so on. Okay, but our motor that we have, okay, which we are using in the lab, is quite requires quite a high current drive, all right, and voltage. So that is why we need to provide this additional power over here. Okay, so this motor driver chip allows us to, I mean, you can think of it as simply amplifier. All right, so whatever signal that comes here, so this is of course 0 volt and 5 volt, but here at the output side is amplified because of the higher voltage that I'm able to provide here. Okay, to drive the current, I mean to drive the motor. Okay, so that is how the H bridge works. Okay, so you use that in the PWM studio. All right, we didn't go too much into it, but it's good to know, so right, so that when you look at it again later on when you're building the robot, all right, you know how to do the connection. All right, so in terms of the code, all right, like what I mentioned, why this code works is because when we configure the bits, okay, the COM bits here. All right, what we are saying is when this is driving in one direction, the other one is 0. All right, when this is going in the other direction, the other is 0. So when it's 0, what does it mean? It means it's normal port operation. So normal port operation means by default it will be grounded. All right, but when it's 1, 0, it is basically having the PWM signal being generated on that particular channel. Okay, so this is how that particular part of your code works. All right, so just to make sure that the pin is grounded, we also write an explicit 0 to that pin. All right, so when one side is having the PWM, the other side is grounded and so on. All right, so this was the PWM studio, all right, that we covered. All right, the other thing is the mapping. Okay, so we in the PWM studio, we are using timer 0, and we are using both channel A and channel B for the two PWMs. All right, so that is of course within the module, the peripheral itself, the registers and so on. But these pins, I mean these pins are mapped to actual physical pins. All right, so how do we know the mapping? We need to look back at the pin layout, okay, of the microcontroller. So when you look at this, you can see that the OCOA and OCOB are both mapped to pin 12 and pin 11 of the microcontroller. Okay, and that is actually port D pin 5 and port D pin 6. So port D pin 5 and port D pin 6 is mapped to pin 5 and pin 6 of the actual Arduino pin. All right, so this again important things to note. All right, I mean this sort of confusion sometimes happens because whether we are talking about the Arduino pin number or the actual port and pin number. Correct. So this is sometimes a confusion when we are dealing with the Arduino boards. Other boards don't have this confusion because other boards you just directly have the port and pin. Alright, but all Arduino boards have their own mapping, correct, to simplify the process. So sometimes you need to be careful which particular reference you are at. Are you talking about the Arduino pin numbers or the actual microcontroller port and pin numbers? Okay, so let's move on to the actual tutorial. Okay, but before we do that, just to make sure you all are awake and active, we will do a simple sort of a quiz, a poll to see your understanding. Okay, so you just need to go to this website. I mean, just go to open a browser and key in this in your as a URL. Okay, so x as a value 0x01, and you have an if statement here that says x and with 0x0f. So will it return true or false? Okay, you answer based on your own understanding. Don't worry about the majority or the other responses. Okay, so I strongly encourage you all to respond. Okay, think about it and respond so that again, right or wrong doesn't matter, right? We are here to learn. All right, so at least you know you're right, or you know you still need to clear up some misunderstanding. Okay, so looks like a very close call between true and false. Maybe I should set similar questions for the midterm. Okay, so let's look at the statement. Okay, so give me a minute. Let me bring up my OneNote here so we can discuss this properly. Okay, so this is important, like I said, because we need to use such techniques quite regularly in our code, especially when you deal with microcontrollers. So you need to really know the idea behind using bit masks and or and things like that. Okay, so let's look at this. So what we are given is that x is equals to 0x01, and I'm asking whether this statement, if x end with 0x0f, will it return true or false? So first thing is, this is an AND operation. Alright, so AND logic we know, right? As long as the input is both the inputs are 0, output is 0, both inputs are 1. Sorry, as long as any input is 0, the output is 0. Okay, only when all inputs are 1, the output is 1. So as long as we know the truth table of the AND gate, the next step is to apply this for the 2-bit patterns here. So one is 0x01, the other is 0x0f. So 0x01, if I put it in binary, is 0000 0001. 0x0f is 00001111. Okay, and I'm going to do a AND operation. So I do an AND operation, only this last bit here will be a 1. The rest of it will be a 0. Okay, so this gives me this answer here, 0x01. So is this considered true or false? Okay, so in terms of binary, in terms of logic, okay, anything that is 0 is 0. Anything is 0 is false. Anything that is non-zero is true. Anything is non-zero is true. That means this is a non-zero value. That means this is considered true. Okay, so this check here, this if check will return as a true result. I will return a true result for me. Okay. So those of you who put as false, I hope you understand why it is true. Okay. If you have any doubts, you can still put in the chat or you can ask me. I can clarify. Okay, so again, this is important. Okay, because it is a very common thing to check for specific bits in a register. All right, and to know whether certain bits are set or clear, we do an AND. If you want to manually set any particular bits, we'll do an OR and so on. All right, so these kind of bitwise AND or NOT operations are very, very common. You see it again and again. Okay, not only in this module, in other modules as well. Okay, so you have to get comfortable with this. Okay, let's try another one. Okay, another one. Okay, so most of you have said it is false. Okay, so let's explore this. All right, to just be sure whether it's true or false. So the same x value, the x is equals to 0x01, and I'm saying that if x and 0x00. Now, before we look at the answer, the first thing you must understand correctly is that this and this are two different checks. They're not the same. Okay, why? Because here is a single AND operation, here is a double AND operation. Okay, and what is the main difference? If I say it is a single AND, you're talking about bitwise operation. If it is double AND or double OR, it is what you call logical operation. Okay, so in logical operation, we treat each sort of parameter as a single true false value. We don't look at it as bitwise. Okay, we don't look at it as bitwise. So this statement here, okay, so x is 0x01, okay, and with 0x00. So we look at each input as a single Boolean value. So this will relate to true because it is non-zero value. This will relate to false because it is a zero value. And this is true and with false. So true and false means is considered one and with zero. Correct? So the answer would be 0, which is false. This is 1 and with 0. So the answer is 0, which is false. Okay, so even though the answer is, most of you are correct, false, I hope you understand why it is false. Okay, it is not because we did a bitwise operation. Okay, it's not a bitwise operation. We are doing a logical operation. Okay, so in a logical operation, we treat each input as a single Boolean value. Okay, and then we evaluate based on the Boolean operation that we are trying to execute. Okay, so there's a big difference between the first statement and second statement. Okay, so majority got this right, but I hope you understand why it is false. It is because of the Boolean operation that we did. Okay, so I hope that has gotten some sort of made you a bit more awake and ready to start the questions. Okay, so let's start with the tutorial questions proper. So firstly, understanding the PWM module. All right, so basically we know that we have 3 timers. Okay, timer 0, timer 1, timer 2. All right, 0, 1, and 2, and capable of 6 individual PWM signals. Okay, why 6? Because each timer has 2 channels, right? Channel A and channel B. Okay, and now what you want to do is you want to consider these scenarios. Okay, so the first thing is describe a software approach to generate a PWM signal that is not dependent on the hardware PWM block. All right, so we know that the PWM signal is basically a pulse, all right, with a particular high duration and low duration that keeps on repeating indefinitely. Okay, and we saw that being generated with the PWM block but now you want to use a software approach to do this. Okay, so to do it in a software approach, basically we just need to keep toggling an output based on the desired on and off time. All right, so in terms of software, the pseudocode is quite straightforward, correct? You configure a pin as output, you set it to 1. Okay, after you set it to 1, then you delay for T on time. So this is the on time, and then you set it to 0 and you delay for off time, and then you loop back to step 1 and you repeat. Okay, so you can manually sort of perform these steps to generate your own PWM, okay, without using the hardware module within the controller. Okay, so it works, right? You can still drive a motor, but what is the drawback? Right, so the major drawback is that you cannot generate, you basically can't do anything else because you're continuously executing the loop. Okay, so when you're continuously executing the loop over here, all right, what happens? You can't do anything else. Okay, you can't say that, okay, in between I want to read a switch or I want to update some other LED. You can't do anything because the moment you do something, the whole timing sequence goes off. Correct, the whole timing sequence goes off. And the other thing is, we also have the concept of interrupts. Correct, so in between something happened and I suddenly jump to interrupt. Okay, then some time will go there. So by the time I come back here, again the timing sequence goes off. All right, so this is again a very inefficient way of doing things. Okay, because basically you are stuck there. Okay, and you can't do anything useful. All right, so this again not at all a desired way of generating PWM. All right, when you use the peripheral block, what happens? Okay, as we have seen in the studio, you only need to do the initial setup code. Once the initial setup code is done, you do not need to do anything else at all. Okay, you don't need interrupt service routine, you don't need anything else. Okay, you can just let the hardware run by itself. All right, there is no need for any other code to be executed at all. All right, it's a one-time setup. Okay, so that is the advantage of the PWM. But one time you set it up, so that's the only few lines of code you need to execute. Subsequently, it is just done totally with the hardware. Okay, so the other scenario is if I do not have any PWM module in the microcontroller, but I don't want to use software-based approach. Okay, like what we saw just now. What are the other options available? Okay, so one of the options available, which most of you should know from EPP1, is your 555 timer. Okay, so I will not go into the details of it, but if you're interested, you can go back to look at your week 4 Studio 1. Okay, those of you who maybe did not do our EPP1, okay, I can share with you all the link where we discussed this, some video that I made earlier. All right, and you can have a look. All right, so basically this 555 timer is just relies on 2 resistors and 1 capacitor. All right, and what happens is there is always this continuous charging and discharging going on through the capacitor, which allows the output to toggle, okay, on and off. Okay, so the duty cycle, okay, or the T1 and T2 are controlled through the resistor and capacitor values. Okay, I will not go into the details of how the 555 timer works. That is not relevant to the I mean, it's not really important for us right now. It's just to show you that this is another option available. Okay, and these are again important, I would say, thought processes that you must understand. That sometimes you start off a project with a particular microcontroller, and then along the way you realize that you do not have everything that you need. But I've seen this before in quite a few students, correct, when they're doing the FYP, where they start off the project using a controller, you know, that they're comfortable with, but you know, halfway through they realize that it doesn't have everything that they need, you know, because they didn't factor this and consider that and so on. Okay, so then they are stuck in a dilemma. Correct, what do I do? Should I switch to a different controller and start all over again, or should I complement my existing design with hardware solutions? All right, so these are important things that can actually help us, right? Because maybe you just needed one extra PWM, okay, which you don't have, okay, and then maybe this might be the only solution available. Okay, so it's always good to have understanding of different options that you can take, okay, if you need to do something. All right, so another scenario is that we want to generate a very low frequency PWM signal. Okay, and even with the largest prescaler setting, the period is still too high. All right, so we know that basically the clock that we have, which is the 16 megahertz, okay, goes through a prescaler. All right, so the prescaler is to divide. All right, so divide. The bigger the prescaler, the lower the frequency. All right, but now we are saying that even with the largest prescaler setting, it is still too high. Okay, I want it to be lower. All right, so how can I mean, the frequency is still not low enough for what I want. So what is the solution? Okay, so one solution is you can consider a software approach to keep track of the number of interrupts. Okay, and then toggle the output pin accordingly. All right, so this is one option. Okay, that means what happens is right now, for example, if I take timer 0, I know that timer 0 starts from value 0, goes up to 255, and then comes down. All right, so this duration here is basically determined by my f clock divided by the prescaler. Correct, so that determines how long I will take to count from 0 to 255. All right, now the thing that we now need to consider is I want this to be longer. Correct. Okay, that means I do not want to overflow and increment my count now. So what I can do is I can use this event here to generate an interrupt. Okay, and in the interrupt I have another variable that I increment. So in this other variable, so I can maybe call it tick. Okay, plus. All right, so if assuming that I want, let's say, a 5-second interrupt. All right, and this count here, the maximum I can stretch it is maybe 1 second. All right, that means I just need to wait for tick to go up to show that it's 5 seconds, has 5 ticks has incremented. Then I know that I have fulfilled the timing gap that I want. All right, so we are still making use of the timer module. We are still making use of the timer module. All right, but instead of directly using the overflow, okay, as a trigger point, I use that to generate the interrupt, and inside the interrupt, I manage another variable. So this variable basically gives me the multiples of the times where the overflow has happened. Okay, so this allows me to sort of make the overall period longer. Okay, so that is one option using the software approach. Okay, the other one is of course using the higher bit timer, which is timer 1. So in timer 1, you have 16-bit timer, so which means that even with the same settings, I will take a longer time, okay, to hit. Okay, so with timer 1, I can hit the value at a much longer delay. All right, so that is what you saw also in the studio. Okay, now let's talk about the interrupts. All right, how interrupts are managed. Okay, so in the studio, you were driving a single motor. All right, now let's assume we are going to drive both the motors concurrently. Timer using both timer 0 and timer 2. Okay, and we have already configured both of them to use interrupts. Okay, so how will it work? If both the interrupts were to be triggered at the same time, what would be the sequence of execution? Okay, so if let's say now I use both the timers, okay, timer 0 and timer 2, and both of them are going to have interrupts and both triggered at the same time, so what would be the sequence be? Okay, so the sequence would basically be the, okay, so if currently you're in the main code, okay, the first interrupt that you will service is timer 2, the other one is timer 0. Okay, why is that? Because if you look back at your interrupt vector table, okay, your interrupt vector table, the sequence is basically the priority. So the timer 2 comes first, followed by timer 0 later on. Okay, which means that if both interrupts would be triggered at the same time, then timer 2 will run first. Okay, timer 2 ISR will run first. Timer 0 ISR will run after that. Okay, so the context switch here is what? The context switch here is like what we discussed before. That means when I am running my code, okay, in last tutorial we discussed this concept. So when I'm running my code, I'm in the middle of something, correct? That means my register values, my program counter, all of this are currently as holding some value. And suddenly the interrupt is triggered. So I need to save my context, okay, which is a snapshot of where I was or what I was doing, and then jump to the timer 2 ISR. All right, then from there I finish up the ISR. When I finish, I need to come back to the main. So that is where the restore comes in. I restore the context. All right, but before I can continue, the controller will tell me that another interrupt has already been registered, which is the timer 0. Okay, so I need to do another context switch again to timer 0 ISR. Okay, finish that ISR, then go back again. Okay, then I can continue. Okay, so that would be the sequence of operation. Okay, when you have both of them happening at the same time. Okay, now if timer 0 triggered the interrupt just before timer 2. Okay, so in this case, what you're saying is if I were to draw the timeline, okay, so at particular this time here, timer 0 happened, and just immediately after that is where timer 2 came in. So very close. Okay, just before timer 2, timer 0 came in. Then the sequence would be timer 0 will run first, followed by timer 2. Okay, because in terms of time, timer 0 came in first, right? Interrupt was triggered first, so timer 0 will execute first, followed by timer 2. All right. Now, this is because the default behavior of Arduino is to disable nested interrupts. All right. So by default, nested interrupts are disabled. So when they are disabled, which means that when I'm in the currently servicing one interrupt, another interrupt comes in, the event is captured. Okay, that means the microcontroller knows that another interrupt has been triggered. All right, but it will not be able to start the execution until the current ISR finishes. Okay, once the current ISR finishes, then only you can do the context switch and eventually go to the ISR that has already been captured. Okay, so that is the default behavior. Okay, but you can override the behavior. Okay, that means you can manually in the ISR enable interrupt again. Okay, so if you manually go in and enable the interrupts again, then what will happen is, okay, you will be able to go from the main. Okay, you initially triggered by timer 0, so you go to timer 0. Okay, but before you finish, timer 2 is registered, so you will jump to timer 2 first. All right, finish up the ISR, come back to timer 0, finish up timer 0, then go back here and then carry on. All right, so that is when nested interrupts are enabled. Okay, so the context switch, okay, if coming back here, okay, the context switch always goes back to the main loop first and then makes another switch back to the next ISR. All right, so that is how it is. All right, but if I enable nested interrupts, then from where I am, which is in timer 0, I can go into do a context switch from timer 0 interrupt to timer 2 interrupt. Okay, so there's a question how to enable nested interrupts. Yeah, so you can do a SCI, which is enable the interrupts inside the ISR. Okay, so by default, what happens is the interrupt bit is cleared, okay, automatically by the hardware the moment you jump to the ISR. All right, and it's re-enabled again when you exit. So manually, if you override it, you set the interrupt bit by calling SCI function, then you can enable the nested interrupts. Okay, so again, these are all, I would say, controller specific. Okay, some controllers may already by default allow nested interrupts. All right, so that is again the behavior that each controller might have. Okay, so before we go on to the next part over here, let's discuss an important thing. Now, in both these scenarios, we're talking about timer 0 and timer 2. All right, and coming back here, the question says that you are driving, the whole idea is you want to drive the motors. Okay, and from what we saw, okay, what you have done, okay, in the lab, we saw that we can, once we configure the module, okay, the module will generate the PWM signal for us to control the motors that are connected, okay, to the output pins. All right, so with that understanding, will the behavior of the motors be affected? Okay, will the behavior of the motors be affected if these ISRs, the way these ISRs are happening? That means timer 0 ISR first, followed by timer 2, or if I were to enable nested interrupts, timer 0, then timer 2, then timer 0, will the, in both this scenario, will the behavior of the motor be affected? Okay, what do y'all think? Any suggestion, any thoughts? What do y'all think? Will the motor behavior be affected because of these interrupts? Whether is it the first scenario or the second scenario? Okay, so to answer this, we need to go back, okay, to the important concept. I think this is a common, I say, misconception. All right, on what is the impact of the interrupt, okay, on the output pin. All right, and if you look at this block diagram, all right, from the data sheet, okay, what do you see? You see that, okay, so this part here is okay, where you set all the basic configuration and your TCNT counts until it matches the OCR register and so on. All right, so when it matches, all right, which is either whether you use in CTC mode or whether you use in PWM mode, doesn't matter. Okay, the key thing that you must notice here is there are two separate branches here. Okay, one is here, one is here. There are two parallel branches that have no dependency on each other. Their trigger point is the same. The trigger point is the same. That is this, when the TCNT match with OCR register. All right, but the outcome is two parallel outcomes, and the two parallel outcomes are what? One is your interrupt, the other is the I'll just call it the output pin. Okay, and this could be your PWM, this could be your CTC mode, whatever, doesn't matter. All right, so these are both two parallel outcomes. All right, and you can have one without the other. Okay, you can have one without the other. All right, so in our studio, all right, when we did the PWM module and everything, we didn't need the interrupt. Okay, we don't need interrupt because the whole idea is that the hardware will generate the PWM signal for me through the configuration of all the registers. All right, but if I wanted interrupt, then I just enable the interrupt. So when the same event happens, I will jump to the ISR. Okay, so you don't need the interrupt to generate PWM or to generate any CTC signal. All right, the interrupt is there if you want to do some software, okay, when the event happens. But if I'm not interested in doing any software, I just interested in the hardware or the output pin signal generated, then I don't need the interrupt at all. Okay, so there are two parallel outcomes happening at the same time. Okay, and you don't need both of them. You can choose to only have ISR, like what you did in Tuesday Studio, or you can choose to have just the PWM, like what we did in the Timer Studio. So you don't need the ISR if you don't you don't need to put in the ISR if you don't need it. All right, so these are two parallel outcomes that will have start from the same trigger, which is when the TCNT match with the OCR register. Okay, so this scenario here, okay, this scenario here will not affect the motor output. Okay, if the motors are driven directly from the hardware itself. Okay, if the motor is controlled through the ISR, then it's different. Okay, then it might have some impact. But if the motor is driven directly from the output pin, okay, from the hardware block, then there is no impact because they are both in parallel. Okay, both timer 0, timer 2, both running at the same time. Okay, so that's the important thing you must understand, that the way the module is designed is, the hardware module is designed is that the interrupt is there and the PWM or CTC pin generation is also there, but they are both separate. Okay, they can be mutually exclusive. Okay, you don't need one, or you don't need one for the other. Okay, so let's okay, so maybe we can take a short 5 minutes break now. All right, we can take a 10 minutes break. Now it's 9:50. Okay, so let's take a 10 minutes break. We'll come back and then we will do part 2. If you have any questions, you can put in the chat first. All right, and then later when we come back, I will address those questions. Okay, so I'll see you all back here in 10 minutes time. Okay, so welcome back. Okay, so let's continue. Let me just look at the questions first. Okay, so the question here is, all right, so I think here, yeah, the question here is asking us if we want to have a very low frequency signal, correct? And after that, the largest prescaler setting, the period is still too high. Okay, so I think there's some. So you can think of it as actually the frequency, right? The frequency is still too high. So what we want is we want a very low frequency signal. All right. So after I do the prescaling, it is still very high. Correct. Okay. So how do I generate that low frequency signal? All right. So generate an even lower frequency signal. That is where the solution that we talked about just now comes in. All right. So there is, I think there's some maybe the interpretation of the English. Okay, so here when we say involve both hardware and software, okay, so we are not saying that the approach must use both hardware and software at the same time. All right, it's just that an approach that can use one approach using hardware and one approach using software. Okay, so it's not an approach that uses both at the same time. All right, so this first idea here that we talked about is to use software. Okay, why software is because we are using the built-in timer block. All right, and just within the ISR, we keep track of the number of interrupts that happen to know that you have hit the desired delay. correct? So that is the software approach, okay, and the hardware approach, all right. So in this case, both of them use, I would say, in a sense, this is a hardware approach because of the using a higher bit timer. All right, so in this case, we make use of another timer, which is timer 1, which is 16-bit timer. All right, so that is why we say this is using a hardware approach. Okay, so I think the idea behind the question is just to have some discussion on how to generate a particular PWM or periodic signal where we are not able to do it with the current hardware that we may have. All right, so if we have another better hardware, like in this case we have a timer 1 with 16-bit timer, then that can help us solve the problem. All right, if we don't have that, then we will need to use some other software approach like this. All right, in the earlier one where we talked about the hardware and software approach here, with the, let me see, where is that? So this one is where we talk about the PWM using the 555 timer. So this is a pure hardware solution. All right, because this does not require any software. There's no configuration of registers or anything. So this is a pure hardware solution. All right, so that is where, so we say this is one way in which we can generate a PWM signal without relying on the microcontroller that you're using. Okay, so there's one more question on contact switch. Okay, so contact switch is okay, so basically in this example, what happened is when your main code is running, all right, when the interrupt, so the first interrupt that happens, when both interrupt happen at the same time, timer 2 is higher priority, so timer 2 will get to run first. So the contact switch basically means that I save whatever I was doing. So at this point of time, okay, when the interrupt comes in, I was busy doing something in the main loop. So whatever I was doing, those registers involved, those variables, the program counter, and all these registers, this information needs to be saved somewhere. Okay, so that is basically what we call the context switching. So I need to save it somewhere, and then I need to load the program counter with the new address of the ISR and then jump there. So that is the context switching. So once I jump there, I finish, I will return back to the main loop. So that is the context switch again. So every time I go is one context switch, I come back is another context switch. Because I need to switch back to where I was before I went to the ISR. All right, so once the ISR, once I come back, then I realize that the controller has already captured another interrupt which is not yet serviced. So I need to do one more context switch to the timer 0 ISR and then finish up and then go back again. All right, then I can continue. Okay, so that was the context switch. Okay, so let's go on to this part 2 first. Okay, so before we go on that, maybe just something to maybe excite you all. I think most of you already know, all right, that we are very supportive of enterprise solutions, and it's students taking up some involving themselves in startups and things like that. All right, so there are a lot of opportunities for you all. All right, within NUS, within SOC itself, there are a lot of grants that you can apply for. All right, if you have some idea, NUS wise, there's NUS Enterprise that also supports this. Okay, so there are a lot of opportunities to turn an idea into something bigger. All right, even if it doesn't grow as big as you want, you can always give it a shot first. All right, sometimes you will learn some things along the way that can help you maybe come up with something better in the future. Okay, maybe just I share something with you all. Maybe I've shown this before. Let me just share this video. You might have seen this video in the orientation, but let me just share again and talk a bit more. Okay, so basically, in that video, what you see is a solution developed by the students, and this was done when they were in year one. That means just like your, okay, that means after EPP one, when they were starting EPP two, they came up with this idea. All right, and then they talked to me and they wanted me to be the advisor. Okay, so so their solution is basically to have a system where in the fridge you put all these trays, and then you are able to keep track of the usage of these your milk or your beverages and things like that. All right, and then to automatically update it, and you give some notification that okay, you're running out of this particular drink or something. All right, so this was their idea. All right, and so they came up with a solution, and as you can see, it's a very simple solution. It's a sensor hooked up to a ESP32, then they have some Bluetooth and some Wi-Fi connection and things like that. And it's something that all of you can do. All of you can do, right? Trust me. Okay? It's not something that is only graduates can do or something like that. Okay, so with what you already have in EPP1 and what you're already learning, you all can easily come up with something like that. Okay, so we went to this NUS enterprise. The students gave a pitch, correct, to ask for funding. Okay, so basically what was the outcome was they didn't get funding, all right, but they learned, I would say, quite a important thing, all right, in terms of what to look out for next. All right, and the main idea, I think the key takeaway that they got, okay, from the panel is that when you come up with a solution, all right, I mean, all of us can come up with very good such engineering solutions. All right, we can take Arduino, we can take some controller, take some breakout board, put things together, and things can work. All right, but the key takeaway was, what is the business aspect of it? What is the thing that will get people wanting to use the product or buy the product? Okay, and I think that is the key takeaway that is usually missing for most, I would say, students when they initially come up with the idea. All right, and it's because you get too excited about the technical achievement that you have made. Okay, you get very excited that you created this app, you created this hardware, and it works, you know, and you're very excited about it. But how do you package it, you know, in a way that appeals to the to customers to want to invest and spend money on it? All right, so I think that was the thing that the key takeaway. But even though they didn't get funding, they got some office space, okay, at the, I think, block 71 or somewhere. All right, to continue to work on the project. All right, so I would strongly encourage you all right, either individually or with a team or whatever. If you have something that you want to work on, you have some ideas, okay, you can just go ahead and try. Okay, submit an entry, go and pitch your idea. Okay, if you get some funding, it's good. If you don't get funding, maybe you get office space, and maybe through the office space you get to interact with other like-minded individuals, and slowly build up something. All right, so you have time, correct, to think of something, and go ahead and pitch. All right, so go to this website, NUS Enterprise, all right, and go and check out some of their systems, or their supporting platforms, all right, funding and so on, and maybe some of it might interest you. All right, and if it interests you, please go and apply. Within NUS SOC also, we have another bunch of similar activities, all right, to encourage startups. Okay, so do go and explore these avenues. Okay, so that is just to hopefully excite you, all right, as you work on the project and get some ideas from it as well. Okay, so let's move on to timers. All right, so this second half is also very similar to the first half. Okay, it's still timers. All right, but only thing is, instead of looking at it from the PWM, we're looking at it in the CDC mode. All right, and so here we have given you the sections of the data sheet, okay, which you need to refer to, okay, to answer these questions. So example of use of timers. All right, so I think the studio, maybe when you do the studio, you can't really appreciate why we want to use timers. All right, because the end result may not necessarily be something that you feel that is so compelling, all right, from the studio itself. All right, but actually timers are very, very powerful. I mean, a simple scenario. Let's imagine that I have my board, correct, and I have two LEDs. Okay, a simple solution. Two LEDs, and one must blink every 3 seconds. The other must blink every 4.5 seconds. Okay, or maybe 4.1 seconds. And this is 3.3 seconds, something like that. Okay, some very funny numbers. Okay, but I need to blink at a particular rate. Okay, and both of them have to keep on running at the same time. Okay, regardless of what other things are going on in your controller. All right, the only way you can do something like this is to use some hardware-based solution, which is basically the timer. Okay, so I need to configure this to some timer 0 or timer 1 or timer 2, and configure the registers to generate some signal that will drive these LEDs while I'm busy with the software. So the software can still carry on as it is in your code. All right, but the hardware can control the LEDs. Okay, so the timers are actually very powerful tools that can help us to manage a lot of activities concurrently, all right, while you are busy with other things. Okay, so for example, just a real-time clock. Okay, so that is one example. Of course, when you go on to operating systems and you learn about multitasking, then you also see how timers are actually used, okay, to help manage the switching of tasks, okay, between the various systems. Okay, so I think the studio doesn't, I mean, you may not really get the full benefit of the timers from the studio, but again, this example tells you that, you know, when you have some requirement where things need to run at some particular rate and timing is important, all right, and you want it to run with that sort of reliable timing without being affected by any other software, that is where hardware blocks come in. All right, so that is where this timer blocks is very useful. All right, so timer 0 and timer 2 are 8-bit timers. So what does the term 8-bit timer mean? All right, similar to, I think last week when I asked you the question, how many bit controller is the Arduino Uno? Okay, so we say it's an 8-bit controller. All right, so when we say 8-bit controller, generally almost all registers are 8-bit. Okay, all registers are 8-bit. So when you read and write to registers, everything is 8-bit. All right, so the timer 0 and timer 2 are both 8 bits, which means you count from 0 to 255. All right, and the largest resolution you can have is basically this divided by the largest prescale value, which is 1024. All right, and so the maximum number of cycles between the increment, all right, of TCNT0 or TCNT1 is 15,625 cycles. Okay, that means when you divide it by 1024, the largest prescale value. All right, so the smallest time interval between increments. Okay, so basically what is happening is you have your 16 megahertz clock. Okay, go through the largest prescaler, which is 1 by 1024. So that will give me this value here, 15.625 kilohertz. Okay, so this 15.625 kilohertz is the frequency at which I'm going to increment by TCNT. So when my TCNT is incrementing, okay, that means let's say this is my current count 0, my next count 1. Okay, so this is 0, this is 1, and so on. So the next count here is 2. So that's assuming that it is incrementing. So the delay between each increment is 1 by 15.625k, which is 0.000064 seconds. So that is the interval between each increment, okay, of the TCNT register. Okay, so when I count all the way, that means if I allow myself to count all the way to the maximum value of 255, so the maximum delay that I can have from 0 to 255, when I count from 0 to 255 is 0.01632 seconds. Okay, so that is the largest interval I can get, all right, if I use timer 0 or timer 2 with the largest prescale value. Okay, timer 1 is a 16-bit timer, all right, as we have seen in the last studio. Now, what one advantage or disadvantage? So now timer 1 is a 16-bit timer, which means that you can go up to 65535. All right, so the largest resolution again is the resolution is the same, right? Because the prescaler values are still the same. So you still have 16 megahertz. Okay, go through 1024. Okay, and then come out is the same. Okay, the 15 point something kilohertz. All right, so that equivalent to a period of 0.000064 seconds. All right, so that interval is the same. The timing interval is the same. From one count to the next count, that interval is the same. Okay, but the only difference is now I can count from 0 all the way to 65535. All right, so that means the maximum time duration I can count is 4.1924 seconds. All right, so I can have, I can configure an interrupt for every 1 second, every 2 seconds, every 3 seconds using the timer 1 alone. Okay, because I can go up to an interval of 4.1924 seconds. Okay, so the registers, all right, basically twice as large, okay, as timer 0 and 2. Okay, which means that you need to have more sort of setup. I mean, in terms of the actual programming, you need to just factor in that you need to maybe configure 16-bit registers, I mean, in terms of the instead of the 8-bit registers. All right. So in terms of space, of course, they also occupy more space on the chip. Okay. So I think the disadvantage is okay, quite minimal. All right. Compared to the advantage that you get. All right. So the advantage, of course, that you have this one 16-bit timer, all right, which allows you to have this large timing interval, correct, which can be quite useful, okay, in certain applications. Okay, so the disadvantage I would say is fairly minimal compared to the advantage that you have, okay, by having this timer on your controller. Okay, now let's look at this question here. So we are given the following contents of TCCR 1A and 1B, and OCR 1A holds the value of 247. Then given that TCND 1 is initially 0 and you're operating in CTC mode, okay, and the all interrupt flags are set properly. So these are the register configuration TCCR 1A and TCCR 1B. So first, let's look at these two registers and understand what these bits mean. Okay, so when the TCCR 1A, if you look at the upper two bits, they are for the COM1A1 and COM1B1. All right, so COM1A and COM1B. And when you set the value of 0, 1, basically you want to toggle on compare match. Okay, toggle on compare match. That means if it is whenever a match occurs, so this toggle mode basically happens, tells us that whenever there is a match, you will toggle. So 0 will become 1, 1 will become 0, 0 will become 1, 1 will become 0, and so on. Okay, so you keep toggling. Okay, the next one is the last two bits, okay, of the TCCR 1A register are actually the WGM bits 0 and 1, and then the TCCR 1B is also have the other two WGM bits. This WGM is the waveform generator bits. Okay, so for TCC timer 0 and timer 2, you have 3 bits. Here you have 4 bits. Okay, if you look back at timer 0 and timer 2, this is actually 3 bits. Okay, and this 4 bits here basically tells us the mode of operation, whether is it normal count up, an overflow, or is it PWM, and so on. So this is this bit configuration 0100 basically tells us that you're going to operate it in CTC mode. Okay, CTC mode. And this earlier configuration says that whenever the match is there, you will toggle the output. All right, and this last 3 bits of the TCCR 1B register is to set the prescaler, which is by 256. So you're going to divide the clock by 256. All right, so you can see that in this configuration, okay, in this configuration, you are directly controlling the hardware. Okay, directly controlling the hardware on the OC1A and OC1B pins. Okay, you're directly controlling the hardware, the OC1A and OC1B pins. So this is automatically what we call hardware driven. All right, so once you configure everything, okay, it will just automatically run, okay, and be hardware driven. So what is the interval between timer 1 compare AVAC, by which timer 1 compare AVAC is triggered? All right, so in this, so how often will timer 1 interrupt be triggered? So that is the question. All right, so since we already said that we have enabled the interrupt, okay, and the prescaler is 256. So the 16 megahertz period will give me an interval of 16 microseconds. All right, that means the interval at which I will increment my count. That means if I were to start off with 0, when I go to a value of 1, okay, this interval here is 16 microseconds. Okay, and then another 16 microseconds later, so 32, then it will be value 2, and so on. Okay, so I'll start off from 0, 1, 2, and so on. Okay, and each time I increment, I will take 16 microseconds to increment. All right, so the period is 247 plus 1 multiplied by 16 microseconds, which is 3.968 milliseconds. Okay, so sketch the waveform on OC1A. So there is a match approximately once every 4 milliseconds. All right, and the COM bits already said that you want to toggle on the match. Okay, so that means that we get a square wave of period approximately 8 milliseconds. Okay, so every 4 milliseconds you will toggle. So first it will go up, 4 milliseconds later go down, and then go up, and so on. Okay, so that is what is happening, or what you should observe on the OC1A pin. Okay, the 4 millisecond is from this calculation here, because each increment is 16 microseconds. Each increment is 16 microseconds. So to go all the way up to 247 plus 1, okay, it will be close to 4 milliseconds. Okay, so it's 3.968, but we say we approximate to 4 milliseconds. Okay. Okay, so there's a question whether we should include the +1 or no need to include the +1. Okay, so yeah, if you look at the lecture slides, there was a +1. Then in the studio, we did not do a +1. And here's another +1. Correct. So rightfully, the +1 makes close to, I mean, if the value is large enough, it doesn't really make a very big difference. All right. So I think for simplicity's sake, you can, the +1 is still the correct answer. Okay, because you are counting from 0. All right. So you need to include the 247 plus 1. All right. So the plus 1 is the more correct answer, I would say. All right. But even if you don't put it, the final answer you calculate will still be very, very close to the one without the plus 1 or with the plus 1. All right. But the plus 1 is the more accurate answer to represent what is really happening. Okay, so in this question 4, we're saying that we want to trigger comp A back on timer 0 once every 650 microseconds. In CTC mode, complete the following table. All right, and we're supposed to round up whenever V is not an integer. Okay, so in this example, we are saying that the N mega is clocked at 20 megahertz. So this is also again something to take note of. So when you're doing the midterm and all, read the question carefully. Okay, so even though the Arduino Uno is running at 16 megahertz, the question may specify some other frequency. Okay, so always read the question carefully to note what is the frequency at which the controller is being clocked in that particular question. Okay, so since we know we're running at 20 megahertz, the prescaler divided by 20 megahertz will give us the period of the timer. Okay, so I'm going to run through just one example, okay, one particular prescale value, and then the rest is the same. Okay, so let's assume we're going to take this, the prescale value is 64. So if the prescale value is 64, that means I get a periodic interval of 3.2. So this number basically is like what we said just now. I start off and I count bit by bit, this one value at a time. So from 0 to 1 to 2 and so on. So this interval is now 3.2 microsecond. Okay, the interval between one count value to the next. All right, so if I want to reach 650 microsecond, that means I want to achieve 650 microsecond from here to here. Okay, so it's basically 650 divided by 3.2, which will give me 203.125 counts. Okay, so now I have a decimal point here. So what do I do? Okay, so the question specified that we round up. Okay, we round up any cases where V is not an integer. Okay, so in this case, we take the 203.125 and we round up to 204. Okay, so that means by hitting a count of 204, we will be able to achieve slightly over 650 microseconds. Okay, so when you set OCR1 and set to 204, you will get 652.8 microseconds, which is slightly above. All right, and that gives us an error of 0.43%. Okay, so that is when we use the prescaler value of 64. Okay, so let's look at other. So we just basically repeat the whole procedure again for all the prescaler values. All right, so this is the answer you should get. All right, so basically for the clock by 1 and clock by 8, okay, you don't have any value because it is too large. It cannot fit into the 8-bit register. Okay, so that is why this is all NA. Okay, so any value that is bigger than 255 is not practical for our timer 0 or timer 2. So the only 3 options are this. Okay, so from this you can see that the value of V will give the best accuracy. So both 64 and 256 give the same accuracy. Okay, while 1024 gives very poor accuracy. Okay, so the smaller prescaler value always gives a more accurate timing. All right, now of course we also need to look at the rounding error. So in this case, both of them give us the same actual period. All right, so in this case, both of them should be fine. Okay, in this particular use case. Okay, so okay, that's the end. Okay, I thought there were some more questions. Okay, so the period here is basically the period of counting interval, correct, between one increment to another increment. All right, but when we look at the final rounding value that we choose and the actual period that we get, all right, both of them give us the same final answer here. That means if I choose a prescaler of 64 and I set my OCR register to 204, okay, I will be able to have a actual period of 652.8 microsecond. If I take prescaler of 256 and set my OCR to 51, I'll also get the same 652.8 as the actual period. So both of them will give me the same actual period, all right, of the timer. So both of them will give me the same result. .2 is the interval of, okay, 3.2 is the interval of the timer TCNT counter. The actual period is the point where the output compare match occurs. That means the output TCNT register has a match with the OCR register. Okay, so in this particular case, 256 and 64 are both the same. So, but generally we would prefer one with a smaller prescale. All right, but in this particular case, I would say both are the same. Yeah, the period here is basically the time taken to increment by 1. That means the TCNT register going from 0 to 1 to 2 and so on. Okay, what is this? This is the period. The output compare, okay, so the question is, where does the output compare match occur? The output compare match occurs, okay, so yeah, correct. That means when the TCNT matches, okay, with the OCR register value. Okay, so whenever the TCNT match with the OCR register value, then the output compare match occurs. Yeah, so this is the period of the TCNT register. Okay, this is the actual period coming out on the OC output compare pin. Okay, so the output compare pin. So if you look at this here, we are operating it in CTC mode. Correct. So every 652 0.8 microsecond, the output compare pin will be triggered. Are they both on the same diagram? which diagram are you referring to? Okay, so this period here. Okay, so if I take, let's say, clock IO 64, when I start from 0, I go up to 1 and 2, okay, all the way up to 204. Okay, so I'll increment by 1, by 2. So this interval here is 3.2 microsecond. Okay, up to hitting the value of 204. When I hit the value of 204, the total time that would have elapsed is 652.8 microsecond. Okay, so the resolution here is basically the period of the TCNT register. That means the rate at which the TCNT register is being incremented. Okay, so the smaller the resolution, the more accurate the timing can be. Okay, so that's why you say the smaller the prescaler, the smaller the resolution, which means I can get a more accurate timing. Okay, because the gap is smaller. Okay, the gap is smaller. So when the gap is smaller, it's easier for me to get a more precise timing. When the gap is bigger, then there is more error like this. Right. So when my prescaler is 1024, I have a very big gap between the count. Okay, so when I settle down on one final count, the gap is very big. The error is very big. Okay, so let me go back to that picture there. Wait down. Okay, so the period is based on the actual period of the OC pin. Okay, here as you can see, is based on the period at which the output pin is toggling. Okay, so the actual period, okay, in our case, okay, would be 652.8 microsecond. Okay, 652.8 microsecond. So that is the actual period at the output compare pin. Okay, the resolution here is the resolution of the internal TCNT register period. Okay. Okay, so there's a question why we never do a +1 here. Okay, so again, the +1 is more accurate, but we are also doing a rounding up by default. Okay, so again, these are not, I would say, when we round up, okay, we are sort of trying to compensate, okay, for any difference or any error there. Okay, so again, the +1 is, you can put it there, all right, and I think the answer will still be very close, whether you put the +1 or you don't put the +1. Okay, the answer will be still very close. Okay, the midterm test that I would say just wait first. I think Colin will send out the announcement soon. All right, so wait for the announcement on the details of the midterm. Okay, does the V value of 204 give the best accuracy? Okay, so in this particular example, both of them give the same accuracy. Right, because both of them will eventually give the same actual period of 652.8 microseconds. All right, so in this example, both of them are equally good. Okay, so TCCR1A register. You are referring to which question? The data sheet. Okay, maybe let me open up the data sheet. Yeah, so it's not specified which is 1A and 1B. Yeah, so maybe probably there is some mistake in the data sheet here, so they missed out the A and the B here. Okay, so yeah, so I don't want to hold everybody back. So we have reached the end of the tutorial. All right, so I'll just answer those who still have questions. All right, if you don't have any questions, you're free to log off. So remember, next week Tuesday is a graded lab. It's the ADC lab. Okay, so the material should be uploaded by tonight. All right, and then you can have a look at it. All right, so those who have questions, you can continue to stay. If you don't have any questions, you can log off, and I'll see you all on Tuesday. Okay, so what will the questions be like for this one? Okay, so generally the past few, not say past few, I think ever since we started, it's always been MCQ. So it's always been it's a mix of MCQ and MRQ. Where MRQ is basically multiple response. That means one question can have a few options that are correct. Okay, MCQ is only one option that is correct. Okay, so it has always been that case for the past few batches of students. Okay, so I expect it to be the same, but I cannot confirm anything yet, right, until Colin confirms the format. Yeah, we should be uploading some additional practice questions to help you all. EBP1 knowledge, yeah, you don't need any EBP1 knowledge. This is purely based on EBP2. That is whatever studios that we are covering here. Okay, so let me look at the. This is a question on the context switch. So which part you don't? So which is the part that is not clear? Okay, so basically the context switch is you save your current context. Okay, so when you say context means when you are running your code at any point of time, you are using some variables, you are using some registers, okay, you're executing some particular line of code. All right. So when the interrupt happens, okay, you need to go and service the interrupt. Okay, but before you can go to the interrupt service routine, you need to be able to save this context. That means what were you doing at this point of time. Correct. So that information is to be saved, and then you need to jump over to the interrupt service routine. So that is basically what we call the context switch. So I jump over to the interrupt service routine, I finish up everything, and then I return again. So when I return, okay, so when I return from the interrupt service routine, I need to restore the context. That means I need to load back the registers, load back the program counter and everything, so I can carry on. Okay, so but in this situation here, you service timer 2, okay, but you already have captured timer 0 interrupt, but you haven't serviced the interrupt yet. So that is why once you come back, so over here you come back to the main, but from the main you need to now go to the timer 0 interrupt and start executing that. So you do another context switch. So again, you need to save your registers, your program counter, everything, and then jump to the timer 0 ISR, continue executing, and then go back. Okay, so that's the final context switch when you go back and you restore everything, and then you continue with the main program. Context switching is basically, you need to, the way you look at it is that it means you are saving a snapshot of what you are doing, so that when you come back, you know exactly where to carry on. All right, so the context switch involves that. That means you save what you are doing, and then you jump to this new place, which is the interrupt. Okay, and then when you finish, you are able to come back. So that is also another context switch, because you are restoring the registers to the original state so that you can continue where you left off. Okay, this context switch is applicable to all interrupts. It doesn't matter whether it's timer, push button, ADC, doesn't matter. Okay, all interrupts, when they are triggered, you always have the same behavior. You have to do a context switch, which you need to save and restore. Okay, this first one is you come back from the timer to the main. Okay, and then you from the main, you need to jump to the timer 0. Yeah, so the first one is timer 2 back to the main, and then from the main to the timer 0. Those are the two context switch there.
Could I ask if the quiz is super internet?
Sorry again?
Is the quiz open internet?
Quiz what? Sorry again, can't hear.
Sorry, is the quiz open internet?
I can't say anything now because Colin has not finalized it yet.
Oh, okay. But
Yeah.
can guarantee we are able to access the Arduino data sheet, right?
No, I really can't confirm anything right now about that, you know. So
Okay.
yeah, the only thing I can say is we have always had it as MCQ and M1Q, so I think we should be following that format. But in terms of access to material and all, I can't say anything now.
All right, thank you.
Hi, Dr. Ravi.
Yeah.
Just now you mentioned the OCNA, right? That like when there's a match, OCNA, let's say, is generating a waveform, PWM, CTC, that kind. Then when there's a match, you can have a separate interrupt also. Then they are what, independent or something like that, right?
Yeah.
So OCNA is, let's say, is generating a on off. Then my interrupt, can I mess with the like that on off thing? Like they want, can they affect each other?
I mean, you can. I mean, you can still manually override and change the settings in the interrupt. You know, so you can still sort of for example, in the interrupt, you can change back to normal port operation and manually change the value of the port pin, even though the timer block already toggled it.
Do you have like example? Do you have an example for like how will we use this? So is it like, let's say,
usually what we do is we do not try to duplicate the same action in both ISR and hardware, right? Because if the hardware is already generating the PWM, then the interrupt can be used for something else.
So something like right now the waveform is generating PWM for a motor. Then at every match, we can, in the interrupt, we do some kind of check, is it?
Yeah, you can use the interrupt service routine to maybe count something or use that information to send some data out on the serial port or something like that.
Oh, okay.
You know, so you since the hardware already is generating the PWM for us, we don't need to have the interrupt replicating or trying to mess with that. The interrupt can be used if you want to sort of keep track of that event for some other reason.
Well, then what's the difference between, or rather, you know, I kind of forgot a bit, but the external interrupt is EIMSK and EICRA, right? Or something like that. The EICR is the one that you can change like the detection of the PWM to on like rising or falling, right?
Yeah, that is external interrupt, correct? So that one is to capture an external event, right? So that one is if I want to capture some positive transition or negative transition, then I use that.
So for if I'm using the timer on the TIMSK, then do I have that kind of like rising falling? Or no, I set it in. Oh,
I mean, currently the mode of operation we are using is the CTC or PWM, and both of them are sort of output formats. That means you are generating a signal.
Oh, okay.
Yeah, so you're not capturing a signal.
You're not really. Oh, okay. You're just generating. All right. Okay. Thank you.
Okay. Okay, so yeah, I'll end the call. I'll see you all on Tuesday. Yeah, so I think that we answered that just now, right? The +1 is not necessary. I mean, the +1 is the more accurate one. But without that, the difference is still very small. The V is the value you want to put in your OCR register. Okay, so I will see you all on Tuesday in the lab. Okay, thank you. Bye.